potentially faster way to construct influence lines for beams and frames is the Muller-Breslau principle. So that's what we'll demonstrate in this example. We'll not only construct the influence line using this principle, but we'll also use the influence line to find the maximum effect of a live loading. The key concepts we'll use are constructing an influence line using the Muller-Breslau principle and using an influence line to determine the maximum possible internal loading. Our beam shown here will support a uniform live load of 60 pounds per foot and a live concentrated force of 200 pounds. And because they're live loads, they could act anywhere, everywhere, or nowhere. So the influence line will help us determine where to place those to find the maximum positive live moment that can be developed at point B. And our beam is supported at C by a pin and D by a roller, so it's simply supported with the cantilevered end out toward A. And here's our approach. We'll start by generating the shape of the influence line. That's what the Muller-Breslau principle does for us. But then we still need to find values in order to complete construction of the influence line. Then once we've constructed the influence line, shape and values, we can apply the loads. We'll figure out where to put them and what their impact is. The moment at B. So our first step is to apply the Muller-Breslau principle to generate the shape of the influence line. To do that, we release the structure's ability to constrain or carry that internal force. So in this case, we want to find the moment at B, so we release the structure's ability to carry moment at B. We still have our pin at C, our roller at D. We then apply a positive internal moment at point B and draw the deflected shape. So that means our influence line has the following shape. Now all we need to do is find the values that go on it. And that's our step 2. Now I could pick just about any point to apply the unit load. I'm going to pick point A. So the unit load will be applied at point A, and we will calculate this value for the influence line. I have my vertical reaction at D, vertical reaction at C. So when we apply the unit load at A and we sum moments about point C, I'll take counterclockwise is positive for this summation. We have the unit load acting through 35 feet. We have the reaction at D acting in the opposite direction through 20 feet. So dy is a positive 1.75 in the direction drawn. Now I'll cut it at B because we need to calculate the moment at B. I'll keep the left piece for my free body. I have my vertical reaction at D, my applied unit load. This is 15 feet. This is 10 feet. We have our unknown shear at the cut. Let's sum moments at the cut. Again, we'll choose counterclockwise as positive. My unit force acts through 25 feet. My reaction acts in the opposite direction through 10 feet. And we have our unknown moment at the cut, MB. Solving, we get a minus 7.5 feet. Minus is a good sign because our value, according to Muller-Breslau, should be negative. Now we'll use similar triangles to find this value. We'll call M. So 7.5 feet over this distance, which is 15 feet, has to be equal to our missing influence line value over this distance, which is 10 feet. So M is a positive 5 feet. Now we have our influence line. We can use it to figure out where to apply our live loads and calculate the live load effect. So our step 3 is to apply loads. And we want to maximize positive moment at B. Well, for the point load, which our problem statement said was 200 pounds, we apply it at the maximum positive influence line value, which in this case is located at point B. So we'll put our point load at point B. And to calculate it, its effect, we take the magnitude of the influence line at that point, which we recall our influence line looked like this. Positive value here, negative value here, where A, D, B, and C lined up as such. So we take our positive value at B times the magnitude of the live load, 200 pounds, for a total live load moment of 1,000 foot-pounds due to the point load. Now how about the uniform load? It was 60 pounds per foot. We apply it. In order to find the maximum positive moment at B, we apply it anywhere the influence line is positive, which in this case is D to C. So we have our live uniform load applied from D to C. To calculate its impact, we have to integrate the area under this influence line, and that's a triangular area with a peak of 5, a base of 20 feet, and we multiply that by the magnitude of our distributed load, 60 pounds per foot, and we get a positive 3,000 foot-pounds. So, we were asked to find the maximum positive live moment at B. And we calculate it by taking the 1,000 foot-pounds due to the concentrated load, add in the effect of the uniform distributed load, and we get a 4,000 foot-pounds, or if you prefer, a positive 4 foot-kips. Let's go back and review how we got this. Our first step was to use the Muller-Breslau principle to generate the shape of our influence line. If we're looking for an internal moment, we have to release the ability of the structure to carry moment at that point, apply the moment, and draw the deflected shape. That gives us the shape, and we know that it's all proportionately correct, but we still need magnitudes. So in this case, I chose point A to apply my unit load. We calculated reaction, cut it at B, calculated the moment at B due to the unit force at A, and that gave us this magnitude. We then used similar triangles to find our last remaining magnitude for our influence line. We were then ready to use it. We had a point load, and it acts at the location of maximum value on the influence line. In this case, we're looking for positive moment, so it had to act at the peak positive magnitude location on the influence line, and so that's where we put our live load, our concentrated load. Then our uniform load acts anywhere that the influence line is positive, since we're trying to find the maximum positive moment. So we put our uniform live load between D and C. We calculated the resulting moment due to each of those, added them up, and came up with our solution. Well done.